Next question, we need to determine how can we stop this process. Yeah. We have to find some point that we should stop. Okay, yeah. We need to determine after a certain number of comparisons, we get to the last element. No more element for us to do further comparison. Yeah. We need to find that point. The question, how to determine that point? All right. Question, at what time should we stop splitting? Yeah. When the data, because you cannot split forever, right? So you have to stop somewhere. So we need to determine the point where we should stop splitting. All right. We need to set up some formula for us to determine that the number of K. What is that K? For the splitting, for the last splitting. Yeah, let's say in this way. Which K gives us the last splitting number? All right. Think about when the data size less than 1, do you need to do further splitting? Data size less than 1, that means the subarray, the remaining subarray can only cover one element, right? No. Cannot cover two elements, right? If two elements, the data size should be greater or equal to 1, right? Yeah, greater or equal to 1. You know, the data size here, we consider the length between two elements. If it's 1, yeah, the difference is 1, that means you may have two elements here. Yeah. Oh, I need to, yeah, let me see. Okay, good. Yeah, still there. All right. Our analysis. Yeah. Only when the data size is strictly less than 1, we can make sure we only have one element left. If one element left, that means we do not need to do further splitting. Only one element. There is no sense to do another splitting, right? Yeah. So this condition tells us that is the condition for our last comparison. Okay? Yeah. So let us write this condition precisely in this way. Yeah. All right. So that means when after K comparisons, the size should be strictly than 1, but after we do K minus 1 comparisons, the size should be greater or equal to 1. That means you need to do one more splitting. Why? Because your data, the number of data items in your current subarray greater or equal to 2. You have at least 2 elements. You can still do one more splitting. Yeah. Now the question, how to find that K? How to find that K? By solving this inequality. Okay, so let's solve this inequality. Yeah. After simplification, yeah, we get 2 to the K minus 1 less than or equal to n less than 2 to the K. Yeah. Then we take not natural log of base 2, right? Because power of 2, we should take a log base 2. Yeah. Then we get K minus 1 less than or equal to log base 2 of n less than K. Can you get the range of K? Yeah. So we can write the range of K. Yeah. here we derive the worst case formula. The worst case. Yeah, because the best case, one comparison, right? After one comparison, we find the solution. That's the best case. But worst case, we need to do many comparisons until there is no comparison needed. That's the worst case. Yeah. So for that K, let's find that. All right. Yeah. So this formula can be translated to this formula easily, right? Yeah. So you move, some numbers from left to right, right to left, you can get this inequality. Yeah. Equivalent to this one. Yeah. But this time we want to describe the K. Because we assume N is known. N is given. N is given. Right? Yeah. And we want to find a formula for K. Okay? Yeah. By using floor function and a ceiling function. Yeah. Floor function and a ceiling function. Okay? Yeah. Can we write an equality way? Yeah, here, this inequality still, there is some uncertainty, right? If you want to find K using this inequality, there is still some uncertainty, right? Yeah. Not very good, not the best one. So we want to find an equality, because with that equality, there is no certainty, no uncertainty. Yeah, everything is clear. Yeah. So we need to write it as an equality. So to get that, yeah, let's start from this original equality. Yeah. Before we take the log base 2, we have this inequality, right? Before the log base 2. Yeah. Why we go back to the previous inequality? Because look at here, strictly less than, we want to tighten. We want to tighten this inequality. Make this inequality stronger. Yeah. Tighten it. Yeah. How to tighten it? Okay. Yeah. All right. Because this part strictly less than, that means if we add 1 to n, then we can make this equal sign. How about that? Yeah, because 2 to the k, that's integer, n is another integer. 2 to the k integer is strictly greater than n. That means 2 to the k is greater or equal to n plus 1, right? At least 1 more than n. 2 to the k is at least 1 more than n. In that way, so we make this improved inequality. This is an improved inequality, n plus 1, less than or equal to 2 to the k, improved inequality. Okay, yeah. Then we take log base 2, so we have a new, so look at this improved inequality. Okay, yeah. This one, we can improve it to log base 2, parenthesis, n plus 1. Slightly better, right? Yeah, because here we can use equal sign. Here, strictly greater than sign. So you can see it is an improved version. Yeah. From this improved version, we can write equality. We can write equality. Yeah. So what's that? The conclusion. For the equality, to determine this k, we have 2 formulas. 2 equivalent formulas. 2 formulas with different forms, but they give the same number. The number should be the same. Yeah. The first formula, K-max, the maximum number of comparisons you need to do. So I call it K-max. K-max equals the ceiling function of log base 2 of n plus 1. We use this leftmost expression, log base 2 of n plus 1, but we take the ceiling function because here less than or equal to k. When you take the ceiling function, you move it up, then you reach that k. Okay, yeah, that's the K-max number. But the second formula, you use the rightmost expression, but you take the floor function. Yeah. So K-max equals 1 plus the floor function of log base 2 of n, and these two formula expressions, they are equal. Okay, they are equal. Yeah, we can prove it. Yeah. All right, we can prove it. If you really want to, practice your algebra skills, you can prove it by mathematical induction. To prove it, you can use mathematical induction. Okay, yeah. Here, I do not do it. Yeah. So we have this formula. This formula is given in our textbook. Yeah, in the appendix. In the appendix of our textbook, you can find this formula. They are equal. Yeah. And this formula can be proved by mathematical induction. Okay? Yeah. All right. So now the conclusion. After this step, the conclusion for best case, worst case, then average case. First, the best case is 1. That's the easiest case. Second, the worst case, we just find the formula. One of the two formulas you can use, one of the two versions. Yeah. They are equivalent. You just pick one. Yeah. So here I picked the second one. Yeah. But for the average case, that's the hardest one. How to get the average case. We need to do calculation for the average case. Yeah. That calculation, you need to do a lot of work. You need a lot of work. Okay? Yeah. All right. The question, can we simply by taking the average of the best case and the worst case in this way? Yeah. We know the best case. We know the worst case. Can we simply, using the average of the best case and the worst case for the average case? Yeah. The answer is no. The answer is no. Okay? You cannot use this formula. If you use this formula, it is less than the real average. This number, you get less than the real average. Our real average is much bigger than this number. Okay? Yeah. Actually, the real average is very close to the worst case. Okay? Yeah. A little smaller than the worst case, but very close to the worst case. Now you can see the average case. Yeah. Not right in the middle. Not right in the middle of the best case and the worst case. It is very close to the worst case. That's the average. Yeah. Yeah. All right. Why is that? Yeah. 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 All right. Here, I can use a simple example. When n equals 7, yeah, I can show you, the average. Yeah, so you can get